Time to start the next talk. Next talk is by Razmik Melikbekyan, senior machine learning specialist from IntelinAir. So go ahead, Razmik.
Thank you. So good morning, everyone. As I introduced, I'm Razmik, and today I will present some real-world applications of machine learning in the agriculture. Yeah, from the title, you should expect that the talk will be more concentrated on the practical side of machine learning, and whatever I will show you is already part of our product. So let's start. First, I will talk about what we are doing as a company, then what data do we have, and at the end we'll talk about the use cases of the machine learning. So what do we do? I will start from this simple graph that shows basically the population growth over paths when it's 70 years, and from this graph you can see that approximately in 2060 we will be around 10 billion people. And what does it mean? Very simple thing, that we need to feed 30% more people in upcoming 40 years, and it's not an easy task. First of all, because many urban Western countries are urbanizing the field areas, so it means that the field areas will not be increased by 30%. And it means that we need to help agriculture to increase its performance, and we as a company are doing so. We are using traditional computer vision together with deep learning, together with some rule-based engine in order to provide some insights for the farmers that helps them to improve their crop performance and increase the yield also. So that's in general what we are doing, and now I will talk about the data that we use, because it's kind of specific data. Yeah. So first of all, in order to be able to do something for some field, we need the field boundaries, the shapefile for the field boundaries. Then we have also the tractor data. The modern tractors are really powerful. They can provide so-called harvest and the planter maps. So I will talk about them in details in the further. And the main data that we have is the aerial imagery. This is the high resolution imagery from the airplanes from 8 to 10 centimeters. We have like red, green, blue near infrared bands, and this is really cool. I will show them. For some of the fields, we have only the satellites data. It's commercial and non-commercial satellites from 50 centimeters to 10 meters. We have as well the elevation maps, which shows the height of some point versus some reference point. As a reference point, you can imagine, for example, the sea level. And we have also the weather information, which is kind of new, and we are still in progress to incorporate it into the deep learning models. So let's start. Before I will show some samples, I will talk about the raster data in general, because I guess many of you maybe not are very familiar with that. So raster data is, in simplest words, is a kind of matrix, where each cell of that matrix is strongly associated with some area on the Earth, and the value of that cell is kind of characteristic of that area. It might be, for example, temperature, it can be elevation, spectral band, or something else. And the size of that area is defined by the resolution of the raster. For example, if I'm saying 10 centimeter resolution, it means that the area that is associated with that cell is on the Earth is a square with the 10 centimeter side. Yep, and here you can see the differences between the resolutions on some specific image. Yep, and the imagery is just one form of the raster data that contains basically the pixel values are the amount of the light or energy that was reflected back from the Earth for that specific area, and then collected by the sensors of satellite or the aerial imagery. Yeah, and a few words about the vegetation indexes. Since people started to use this satellite imagery, it was started to become popular. There was some research, and in order to understand how we can measure the vegetation using the imagery, so they came up with so-called vegetation indexes. One of them, very famous, this normalized difference vegetation index. Here you can see its formula. It takes the range values from -1 to 1, and if it's value above 0.5, you may say that the vegetation is healthy, and below, then it's more or less stressed. So this is about it, and we are quite often using this kind of vegetation indexes in our analysis. So a few words about the field sizes. So you can imagine that some of the fields in the US are really big, so they can be around 2.5 kilometer squares, which is around the same size as the Yerevan small center. So of course not all the fields are this kind of big, but there can be even bigger fields. Okay, so that's kind of introduction. Now let's see what data do we have. So this is a kind of small field, not very big, only 43 acres. Just to give you some insight, so it will be around 25 football field sizes, so it's not the biggest one. It's airplane image, RGB 10 centimeter, and together with its field boundary, these blue lines are the field boundary. And in order to get sense, what does it mean, these 10 centimeters, you can see the zoomed version of this. So you just can take this slide and zoom in this picture, and you will, from that part, for example, you will see something like this. So you can see the crop on the field, the rows. So basically, this is really good data to provide some kind of analytics, to do some deep learning, and etc. Yeah, this is the same field on the same day, but the combination is near infrared green-blue. This is so-called SEER, or the colored infrared. This shows the amount of the biomass on the field. This is the same field on the July 4th, so you can see that the field started to, the crop started to grow, and it's everything already green. The same field on the August 6th, but it's already the satellite data, 10 meters, so you can see like the difference, that it's much less detailed than the high resolution data. This is the NDVI map, yep, and it's heat map on the 4th. This is the elevation map. Here you can see the relative heights between each point. So for example, here you I guess here this is kind of waterway, and then you can see that close to this waterway the heights are smaller, so it's kind of really something like this. This is the tractor data. This is the planter data, 20 centimeters. Basically, it shows that from each part of the field, 20 centimeter squares, it shows the amount of the seeds that the tractor put on the ground. Yep. And the same for the harvest. So this is the opposite that the tractor collected from the field. Yeah, this is kind of really nice data. And here you can see basically how the field is changing throughout the season. That it was not planted, then it was planted, then this is replanting because of some reasons, and then it's starting to grow. You can see these replanted areas. And then this is dry down, and this is harvested, and then it starts again. So we have, for each of the field, we have almost bi-weekly this kind of imagery, and we can provide like full season different kind of analytics for them. So that's all about not all. Yeah, a very important point that we as a company, we have open source data. The most important are, I guess, this agriculture vision, which was supported by the paper in the CVPR, and I guess Rand is the co-author of that. It's a kind of semantic segmentation data with 9 different classes, so you can see like these annotations, double plant, dry down, end row, so on. Yeah, we have also other 2 data sets which are much smaller, core calendar counting data set. It's about then when you take a picture of the corn, and you have the number of kernels that on the corn. So we are using it for kind of yield estimation process, and also we have the nutrient efficiency. So all of them are open source. You can go and play with them if you want. So now let's move to the machine learning part. Sorry, and the first one, which the model project I will talk is about so-called non-managed area detection. So as always, there is some data which is noisy, and we have also that kind of data. So for example, here you can see the boundary files that is noisy. So inside the field we have this waterway which should be excluded. this area and also this area, probably some stuff from that year. Yeah, you might say why it's the problem. For example, if we run some width detection model which tries to find the widths on the field, it most probably it will find some widths close to this waterway, but it's okay from the width detection model, but for the business perspective it's not fine because it's basically not non-field area, non-managed area, so we should exclude everything like this before processing our analytics pipeline, let's say. And here you can see another example, which much worse, I guess. So we need something to clean this. Yeah, you may say why we cannot do it manually. Okay, if we have 100 fields or 1,000 fields, yes, but if we have around 80,000 fields, it's kind of difficult to do it, so we need to do something automatic. Yeah, about the data set that we use, so our annotators annotated around 28 fields throughout all the season. So we used RGB plus near infrared and the plus elevation. Here the elevation makes things easier because close to these waterways, as you have seen, there is the relief change, so it helps. We are using quite often the super annotate platform, and the data is kind of imbalanced because only 10% of the data is non-managed areas. You can see like some samples from the training side. Yep. From the deep learning perspective, it's a traditional semantic segmentation task where you should predict for each of the pixel its class. As usual, there is this UNet, which comes when you have the semantic segmentation task. So it's kind of, I will not go into many details, encoder part, decoder part. On the encoder part, the network is learning so-called features, and there is this downsampling. And in the decoder part, there is this upsampling blocks, and there is this skip connections, which helps to keep the spatial information in the upsampling part. Yeah, people always modifying. There are different modifications of the UNet. We are not exception. We use some kind of this kind of version. So we have an VGG16 as an encoder, pre-trained on the ImageNet. Then we change the bottleneck to use some kind of dilated convolutional layers. And in the upsampling side, we have replaced the upsampling layers with the transport convolution layers. A few words about this changing of the bottleneck, why we did it. So since we are doing the image segmentation and we want to do this kind of dense prediction, let's say, for each of the pixel, we want to have the receptive field as much as bigger. Yep, and in order to do that, we did these dilated convolutions. So here you can see that by just adding this dilation, we can keep the same amount of the parameters, like 3x3 kernel. We just added some zeros, so it's added some zeros here, but the receptive field is increased from 3 to 5x5. Yep, and here you can see the architecture of this cascaded dilation. Okay, some results. So we trained using Adam optimizer with cosine and learning rate scheduler. The loss was the combination of the binary cross entropy plus dice loss, which helps to fight against the class imbalance, and some results in terms of precision and recall. You can see the results are quite high, and some samples on the unseen data. Yeah, for example, here you can see this green part, and it was removed by the network. And some other sample, and here you can see that the network is working. Yeah, so now it's on the production, and when the field is coming, it's running, masking out whatever is not filled, and then the rest is running. The second model, it's about so-called field classification. As you have seen, like field is running through different stages throughout the season. So we have defined with our agronom six stages, and for each of the stage we have different, let's say, analytics to provide it to the farmer. And it's crucial for us to know when we have the imagery in which stage the field is. So it's kind of typical image classification task from the first glance, and it should be easy. A few words about the data set. So we used RGB, near infrared, and NDVI. And you can see here the class balances, these two are less. And since it's very important, task, we run some kind of extensive testing on the manual flights. So as I mentioned, it might be from first glance very easy problem to some extent, but since the classes in our case are ordered, we want to avoid the situation when the model, for example, says it's harvested, but in actual case it's not planted or it's planted, because they are, in that cases, the fields are very similar. In some cases, people cannot differentiate it also by A's. So initially we tried with some simple convolution stuff. It was not working properly. So if you imagine this diagonal matrix of the confusion matrix, we want two errors to be close to the diagonal. So we did something which people are doing for the video classification. We used so instead of giving just a single picture, single imagery, so we gave to the model also the previous imageries from the previous slides, and we have the CNN as a feature extractor, and then the LSTM, which is handling this temporal part, the order of different dates imageries, and then we have the classificator layer, which is doing the classification for the last layer. And it was working much better than the single convolution stuff. And here you can see some numbers. It's not ideal, we are going to improve it, but for the current moment it works quite fine. Yep, and the last one is the crop yield forecasting. So for the farmers, it's essential to know how much crop that they will collect at the end. So here you can see data sample. We have the near infrared and RGB, and we want to predict this harvest map in the downside. Yep, a few words about the dataset. We resampled dataset to 20 centimeters. We have this tile size 512, and some words about the train validation sizes. So what we did initially, we did something very simple. So we have created some features from the imagery, like NDVI mean, standard deviation, histogram, and for some other bands, and then run some gradient boosting. Basically, it works quite fine. But the problem is that for each of the tiles, it does one number, predicts one number. So you can see like how the prediction looks like in this case, if we have the light GBM. And here you can see the prediction versus actual graphs and also residuals. And yeah, just here the mean absolute percentage error is 10%. So it works quite fine. But eventually we want to have the pixel-wise regression using the deep learning. So we trained a bunch of different architectures with different encoders. And here you can see that we are able to get from 6 to 7% error rate, mean absolute percentage for the test set. Yep, and here you can see like how it will look like if we use this ResNet unit architecture. Its prediction. It looks much better than the other one. And a few words about the nutrient deficiency. We have some other model which is predicting the nutrient deficiency for the different sizes of the area. And the idea is the following, that since on that area there is nutrient deficiency, it might be possible that, not possible, but in reality from that areas you should expect to have less corn or soybean. So we try to put the model, this model output to as an input for the other model, and it works quite fine. So for example here, if you see this number, 7.79, and if we put this into as an input, then we can get something around 6%, which is like around 2 percentage point improvement. And here you can see some sample from it. Yeah, for example, this is some field that without nutrient deficiency, it's not working properly, but when we are adding it, then we have like much better prediction. The error rate is going down by around 12%. Yep, and this is the last slide. Basically, it's already on the product, and this is how our farmers can see it. The yield forecasting, the numbers, and its heat map. Yep, this is basically all. Thanks, and please questions.